I am Anil Kumar. Welcome to my series on sequences and series. In this video, we'll talk about Koch snowflakes. In the honor of the scientist, we have the name Koch, and snowflakes is the structure which we're talking about. So here we will show that the area of Koch snowflakes converges to 8/5 of the original triangle area. Let's give some background to what this is all about. So we begin with an equilateral triangle, right? So let's say this is our equilateral triangle, and then each side is divided into 3 equal parts. So let me sketch the next stage for you, and then we'll talk further. So to make this series, what we do here is that each side is divided into 3 equal parts, right? So once you divide that, then we make triangles at each end. So we make a triangle at each end. So these are also equilateral triangles, right? These are also equilateral triangles. And so we have a structure which is kind of like this. Does make sense to you, right? Now again, we'll divide each of these portions. So we'll have triangles at each point, which I'm marking here. Is too complicated to draw for me, so I'll leave it there. So the idea is, if I continue with this pattern, I get snowflakes type of a structure at the end. Now we'll try to analyze this particular structure. So as far as the number of sides are concerned, we can see that there are 3 sides, right? Let's talk about number of sides. So in the first pattern, we have 3 sides, right? All equal. Now, number of sides here will be how many? Let's count. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So here we have 12 sides. What we did was that each side was divided into split into 3 equal parts, and then we projected it out as a triangle. So basically we got 3 times 4, right? So each side was divided into 4 equal lengths as shown here, right? So we have 3 times 4 number of sides. So in the next pattern, we expect that to be 3 times 4 times 4, or 4 square, right? So which will be, number of sides here will be 4 times 12, or 48, correct? So if we generalize this and go to the nth, iteration, where we are saying this is our first iteration, right? So this is our first, this is second, right? So slightly different nomenclature than we use in geometric series. In geometric series, we start with 1. Now we're considering basically what are we adding, right? So we are starting from here. We are adding 3 more triangles on each side so that each length is exactly same, right? So what we notice here, that the number of sides which we add are equal to 3 times 4 to the power of n, where n is the nth iteration. Do you understand? So from here it will be n plus 1, okay? Correct. So we have those many sides. Now that is clear. Now what is the length of each side? Now here, let us say that the length of each side is, let us say x. So let's take a general value x. So length of each side is x here. Here the length of each side will be, since we divide it into 3 equal parts, it will be x times 1 over 3. Correct? So the next one, the sides again were divided into 3 equal parts, so it will be 1 over 3 square, and then for the nth iteration it will be x times 1 over 3 to the power of n. So that will be length of each side. So now we know number of sides and length of each sides. So from these two, if we multiply them, then what do we get? We get perimeter, right? So perimeter is product of these two, right? Perimeter means you have to multiply these. So the original perimeter, if it is 3x, then the second one will have 12, which is 3 times 4, right? So I will write this as x times 3. This is 1/3 of x times 3 times 4, correct? Here it becomes x times 1/3 square, right? That is the length of each side, and this is 3 times 4 square, right? Right. And the general term will be, we can combine these terms, you see, to the power of n to the power of n. So let me write this as 3x and 4/3 to the power of n. Does it make sense to you? Now if you see, if I put x as 1, if I put n as 1, I do get this 4/3, right? So let me show you what exactly we are getting into, because it could be very confusing at times. So here it is 3 times x, the perimeter. In this case, we'll rearrange. We say 3 times x times 4/3, right? We took this here. Here we're bringing this 3x times 4/3 whole square, and the general term 3x 4/3 to the power of n. This is after n plus 1, nth iteration. So starting with a triangle, that becomes n plus 1th term. Perfect. So the perimeter gets multiplied by a factor of 4/3 whole square. So the initial perimeter is 3x. For each iteration, it gets multiplied by this factor. Perfect. Now clearly what you notice here is that the perimeter is always increasing, right? So here it is very clear that perimeter is increasing by a value which is by a factor of 4/3, right? So which is greater than 1? So that means it is divergent. So it is a diverging series. And since it is diverging series, this perimeter becomes infinitely large. So that means that we have infinitely large perimeter as n approaches infinitely large values, right? So if n approaches a large value, infinitely large value, since 4/3 is greater than 1, the perimeter is going to be infinitely large. So for the snowflakes which we are talking about, as n approaches infinitely large value, the perimeter unboundly increases and it is infinitely large. Now let us check the area of this system. So now we'll talk about area. What happens to the area? This is what we'll look into in the next part of the video, right? So we have understood one thing, that the perimeter increases infinitely, right? So we can conclude here, perimeter increases infinitely. And now we'll talk about area. The question says that the area is 8/5 of the original triangle area. So that is a part now which we are going to look into. Now let us focus on area. So let me again draw the triangle we are working with. Let's say this is the equilateral triangle, and we want to make this series by dividing this equilateral triangle into 3 equal parts, like all the sides, and at each end will actually make up a triangle, right? So basically that is how the diagram may look like. We don't consider these lines, but we connect the vertices and form the next structure. This step of dividing into equal parts and then making equilateral triangles results into snowflake structure, and we need to figure out that as we continue, perimeter increases unboundedly. It approaches infinitely large value as n approaches large. However, we want to prove that the area is converging to 5/8 of the original area. So let's also try to see how to calculate original area. So let's call this area as A0, right? So area is half of base times height. In this case, let us say we'll take this side as x, and if I drop the perpendicular, in that case this will be x by 2, right? These sides will be equal, and let's say the height h will be equal to square root of x square minus x by 2 whole square. So that will be equal to x square minus x square by 4 square root, which is 4x square minus x square by 4 square root, which is 3, right? So x square can be taken out. So we get 3 over 2 square root 3, right? X square. So that is also a standard formula. You know your special triangle 30, 60, 90, and you know that, correct? So basically we can say that the original area is half of base is x for us, okay, and the height is square root 3 over 2 times x, and therefore this particular area is equal to, let me write it bold for us, and we will say that the area of our triangle A0 is equal to square root of 3 over 4 x square, right? So that becomes the general formula for the area of our original triangle. Now what we have done here is that we have done the first iteration. So I'll call this as my adding more triangles. So I'm saying adding one time, right? So the first iteration is, we see that we have 3 more triangles, correct? So in this particular addition, so what is the addition? On first iteration, as far as the number of sides are concerned, what number of, let's say, number of triangles added? See, the original area is already A0, right? So we know that this particular area inside is A0, right? So we know this area is A0. Correct. So we know this area is A0. We are now interested in finding what is the additional area. So every time we are adding a triangle on each side, the area increases, right? So that is what we are checking, by how much is it increasing. So number of triangles added is how many? Well, last time we had 3 sides and the triangles are 3. So in the first iteration, we added 3 triangles, right? So we added 3 in this case, and each side length of added triangle is 1/3. Do you see that? So each is 1/3 of x. So original was x. Now each side length, all these sides are x by 3, correct? Since we divided x into 3 equal parts, so x by 3 is each side. Perfect. Now if that is the case, in that case, area of added triangles is how much? Well, the added triangles area will be 3 times because we added 3 triangles, right? 3 times. Original, we can compare this with original triangle, right? So if area of big triangle is A0, what is the area of this triangle? Since each side is 1/3, area of each is A0 by 9, 3 square, correct? So area of added triangles is 3 times because we have 3 additional triangles times A0 by 9. Since area of each added triangle is 1/9 of the original triangle area. How did we find that? Since each side is 1/3, so that implies what? Each area, let me call that area 1, each area, this area, is equal to total area A0 over 3 square, which is 9. Correct? So we got a formula in which we can actually work out the general formula for added triangles area and then solve for infinite series. You get the idea. So with this concept, now we are going to move. So now let us once again look into our series. We begin with an equilateral triangle and we add triangles on each side, but the sides are divided in length to 1/3. Since you divide each side by 1/3, area of the new triangle will be 1/9, right? So the structure which you're going to get will have more triangles but less area, correct? So if you compare with this, so we have to look into two things, and that is, first is number of additional triangles, and second thing which you have to look into is area of each additional triangle, and then we'll look into total area, correct? We have already said that the area of the first triangle is A0, where we found that A0 basically is equal to the area of a triangle, which is square root 3 over 4 x square, correct? Where x is each side length, right? So we have done all that. Now let's look into number of additional triangles. Additional triangles, we are interested in only these additional triangles because that area is getting added up, right? So you notice here that the additional triangle in this term, which is actually this is the first term. Let's talk about infinite geometric series. This becomes our first term, that becomes the second term, right? So it all really depends on the number of sides, right? So it is 3 times, because there are 3 triangles, 3 times each number of sides. So it is number of additional triangles is always equals to, in this case, it is 3, right? Which I could also write in general. So let me write a general formula also. When we extend it to n, right? So it becomes 3 times 4 to the power of n minus 1. Because the number of sides, as you see, they are 12 here, right? So basically we did this calculation earlier. Let me write down number of sides here. Number of sides. 1, right? Sorry, in the first case it was 3, and in this case it was 3 times 4, right? So the number of sides are getting multiplied by 4 each time. Is it clear? Since number of sides get multiplied by 4 each time, we get 4 to the power of n minus 1. So in this case it is 3 times 4 to the power of 0, right? And then we'll have at the end, when we do n minus 1, we'll get our result, right? So that is how we are trying to generalize it. So the first iteration will have 3 additional triangles. Then the next one will have 4 to the power of 1 times, that means 12 additional triangles. So based on these 12 sides, we have 12 sides here, right? So the next will have additional 12 triangles, because on each side they will have triangle. Do you understand? So on each side here also, so we have 12 triangles. So in the next iteration we'll have, so in general the formula will be 3 times 4 to the power of n minus 1. The second important thing to look into is area of each additional triangle. So additional triangle area will be equal to the original area divided by 3 square, right? So because 1/3 of each, right, so divided by 3 square, which is 9 basically. So we get additional area of A0 over 9. Perfect. So that becomes additional area. So in general, if we have more number of triangles, in that case the additional area will be A0 over 9 to the power of n. So in the first case it is additional area of each triangle. Is that clear to you? Now we have to now get the total new area added. So let's figure out how much is the new area added. In this process. So the new area added will be multiplication of these two, additional number of triangles and area of each triangle. So will be additional triangles times area of each triangle added. Is it okay? So product of these two will give us the general formula of how many will be there, right? So in general, that will be equal to, we can write this as, this expression could be written as 3 times 4 to the power of n as 3 over 4 minus 1 and 4 to the power of n, right? So that is the general expression. So multiplying these two, we get our expression as 3 over 4 times 4 over 9 to the power of n times the original area. How do we get this expression? We get this expression by multiplying these additional triangles with area of each additional triangle. So if you multiply them, what do you get? Let's do it. 3 by 4 times 4 to the power of n times original area becomes this basically, right? General form n 9 to the power of n, correct? So when you combine the term, you can take these two same, right? So in the same bracket, so 3 by 4 times 4 by 9 to the power of n times the original area. Is that clear to you? So that becomes the additional area, right? So when that is the additional area, in that case, what is the total area? So total area is original area of the first triangle plus, in general, all these should be added, right? So all these will be added. So the value of n is getting added. So we can use a parameter, let's say k. So from k equals to 1 to n, for this value, 4 over 9, or I mean, we'll take 3 over 4 as a constant outside, right? We'll take 3 over 4 as a constant, n is this value, right? Times A0 also I could have taken outside. Okay, so of each triangle, so in the first case n will be 1, so we'll get the area of this additional triangle. In the second case, those which are outside, perfect. So we are adding area of added triangles to the previous one to get our expression. Is that clear to you? Right. So this is a very important expression to understand. Right. So you could actually rearrange this, and we could say that A0 is common, and what we get here is 1 plus 3 over 4 sum of all the additional triangle areas, k equals to 1 to n, of 4 over 9 to the power of n. Right? You can expand this series and add it using the geometric series. And then we'll find this expression will converge to 5 over 8. So you can take this as an exercise, and I'll further continue to show you how. So let me write down the expression which we just got of total area. So total area was original area A0, right? So we have this bracket 1 plus, we had 3 by 4th of sum of a series. We are saying from k equals to 1 to n of 4 over 9 to the power of k, right? So we add this up. So that is what the total area is. Now let us see how to sum it up and then find the answer. So let us expand this series now. So if you expand this, you get A0, within bracket we have 1 plus 3 by 4. If k is 1, we get a term 4 over 9, right? Plus the next term will be 3 by 4. And now k is 2, so we get 4 over 9 whole square. And then we get 3 over 4, 4 over 9 whole cube, right? So like this, the series continue till infinitely large value, right? So it is an infinite series, correct? Now look into slight calculations here. We could actually simplify this a bit. We could cancel these 4's, right? And we could write this as 1 over 3. Does make sense to you? So I'll do this calculation, simplification of what we have, original area, and we have this as 1 plus. So if I cancel 3, goes 3 times in 9, 4 goes, we get just the term 1 over 3, right? So we get 1 over 3 here. The next expression, I could write this as plus. Let's go a step further and I show you the calculation. It is 4 over 9 whole square. So it is like 4 over 9 times 4 over 9, right? So this portion, 3 over 4 over 4 over 9 is 1 over 3, right? So this portion, you could cancel it as 1 over 3, correct? Times 4 over 9. Similarly, the next expression will be, you can write this as 3 over 4 times 4 over 9 times, we can now write this as 4 over 9 whole square, right? 2 of them, and then we can continue this series. So you get that this is now 1 plus 1 over 3, and this is also 1 over 3 plus 1 over 3 times 4 over 9 plus 1 over 3 times 4 over 9 whole square plus so on. Correct? So what you notice here is that in your series, you get the terms as equal to A0, the original area, right, whatever it is, and then first term is, we can write this as A0 plus, then we have A0 times a series which starts with 1 over 3, and then each time to this term 1 over 3 we are multiplying by 4 over 9, right? This is to the power of 1 plus 1 over 3 4 over 9 to the power of 2 plus so on. So that is an infinite series, correct? Now for this sum of infinite series, we know the formula that sum of infinite series is basically equal to A over 1 minus R, provided that absolute value of R is less than 1. So in our case, we have 4 over 9 and that is less than 1, and therefore we could use this formula. Is that clear? So applying this formula, we get the original length, original area plus this series. Here the term A is 1 over 3. So 1 over 3 over 1 minus 4 over 9. So this could be written as A0 plus A0 times, now 1 over 3, let me write like this only. And then we have 4 minus 9 minus 4 over 9. Is it clear? Now that is the original area plus A0 times, that 3 comes here and 9 goes on the top. Or you could also cancel this, right, by 3. But let me write this like this, 1 over 3, right? And here we have 9 goes on the top, and 9 minus 4 is 5. Right? So what we get here is A0 plus A0 times. Now this goes 3 times 3 over 5. You can add this, right? So we get original area common, and you get 1 plus 3 over 5, which is equal to A0 times 5 plus 3 over 5, or is equal to A0 times 8 over 5. Does make sense to you? Which says that the total area now is equal to 8/5 of the original area A0. Is that clear to you? We also calculated that the original area A0 in this particular case was equal to square root of 3 over 4x squared, where x was side length. Is that clear to you? So that is how we can actually prove that this series converges and the total area is 8/5 of the original area. I hope that makes sense. Feel free to write your comment, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.